Hello guys, so today I will be talking first a few talks on Multicast. Today it'll be a bit of a technical introduction into IGMP and a bit of a very brief overview of Multicast as well right at the start. So to start off with, obviously, it's probably best to start off with the type of data flows that we have in our networks. So as we know, very commonly, we have unicast flows. So they are point-to-point, usually between one source and one destination, used for probably a large percentage of communications over networks. You then have broadcast traffic that is usually used on a layer 2 network to reach all the devices within inside a local network. Basically means an all-host group in a multicast terms. It's usually defined by the last IP in the subnet range, and you send traffic towards that, and in theory it should be flooded by a switch and accepted by all of the relevant devices in the network. They'll then process and do whatever they want. And then you finally have multicast, obviously the topic of the talks. It is usually point to multipoint, but you can do multipoint to multipoint in some cases, technically. Not really advised, I would say. It's defined, though, by a specific set of IP ranges, destination IP ranges, reserved specifically for multicast addressing. So if you did go and use one of those addresses as your address on your laptop or your PC, it wouldn't work because it is specifically assigned for multicast. It is used in some kind of protocols for control traffic, but mainly the main use that we see it is obviously for media applications, so streaming video flows over a media network. And in general, there is the range that I've identified here that is available. Some of them are for specific uses, some of them are for general use, some of them are for public use. I'll get onto that a little bit later on. So this is what it looks like. If you're trying to unicast from one source to multiple destinations, you end up with, in this case, we've got 3 destinations. You end up with 3 copies of the traffic coming from a single source and being, utilizing the links throughout the network, which obviously isn't as efficient as possible as it can be. You then have broadcast. Well, that's only inside the layer 2 domain. So in this case, we're flooding with inside these layer 2 switches, and all these destinations are receiving that traffic. But this is where then multicast comes in. You only have to send one copy of the traffic throughout the network, and in theory, it will be replicated at the relevant points so that the source and the source network doesn't have to handle multiple copies of the same content. So if this was a 10 gig flow from a source and you had 10 destinations, you wouldn't have to have a 100 gig link here to support 10 copies of a 10 gig flow, for example. Just have your 10 gig flow onto the switch and then distributed throughout. That then works both at layer 2 and at layer 3, so switches and routers can support this multicast to make sure that it isn't utilizing bandwidth where it isn't needed, basically. The fundamental building blocks of multicast, what do you need to basically make it work? As I mentioned, we need address ranges. They basically identify that it is multicast traffic, and in some cases they can actually identify its specific types of multicast traffic. So for example, source-specific multicast as a good example. You also then need a registration method. You need some way of the network saying, or the host, sorry, saying to the network, hey, I want this content, I want this stream. And that's where IGMP comes into play. So there's various versions of IGMP, and we'll go on to them a little bit later. But in essence, IGMP is there to register an interest. It allows an end host to signal that it's interested in that specific multicast group that it's requesting for. And also network switches can snoop that traffic to be more efficient. So they can prune traffic from specific ports to reserve the bandwidth. This also then obviously links into then the wider decisions of routing. So usually you have a routing protocol to control how you forward Unicast traffic, for example. So you have OSPF, BGP, ISIS, so on and so forth. In this case, usually what we use is PIM, protocol independent routing. Its main job is to route multicast traffic throughout a network to relevant requesting routers. And there's different types of PIM. There's sparse and there's dense. We'll get onto that in another topic. Another talk later. But PIM is there to support multicast forwarding over a layer 3 network, basically. There is, in theory, extensions to OSPF to support multicast traffic, but it doesn't really scale properly and it's never really taken off that well. Then we also have loop prevention. How do we prevent flooding traffic constantly around our network and ending up with a storm of traffic? Well, that's done with reverse path forwarding. And I don't think I'll get into it today, but in theory, what that does is basically checks to see where you've received the traffic from and identify the source of the traffic, the unicast source address of the packet, the multicast packet that you've received, does a routing lookup, a normal unicast routing lookup for that source IP, and then says, where can I reach that from? What port is it? Oh, it's port 1. Did I receive the traffic from port 1? Yes. Okay, accept. If I didn't, if I received it from port 2, block that traffic, drop it. That's the whole concept of RPF checks or reverse path forwarding. So, as I mentioned, we have the need for multicast ranges, and there are some reserved ranges, as you can see here. I will genuinely be reading off the screen for this section because it isn't something that I've been able to memorize myself. But there's blocks for local layer 2 use only. So those are for usually the well-known kind of control traffic like OSPF control traffic, for example, or some other protocols. There is also then a specific range reserved for random use in applications. An example of that is session announcement protocol. Basically, that works. Basically, what it does is it announces conferencing. So video conferencing systems, they use session announcement protocols to then advertise, hey, I have this conference going on, you can join here, and that's done via multicast. You then have a source-specific multicast range specifically for source-specific traffic. And the reason why you allow that is because then you can reuse addresses if source IPs are different. So if you have a source IP of 1 and a source IP of 2, those two different ones can use the same exact multicast range, multicast address, and have completely different content, and it will still work perfectly fine. You then have a glop range. I don't know what that stands for, but it is technically called a glop range. It's assigned, basically what you have is, if you have a /24 range that you own, you will then take, how do I explain this? It's a little bit complicated. It also links in with your ASN. So it links slightly with your /24 that you have and also with your ASN to then form effectively a unique multicast address that you own for your ASN and your range that you have. Obviously, they are globally unique, so they allow you to have those ranges. The only issue with this is obviously if you have a 32-bit ASN number, you don't have a glop address assigned to you. That is the only issue with that. You then have unicast-based addresses. So they use the first. So this gets around the issue of the 32-bit ASNs not having support. You have a unicast-based addresses. So they use basically the first 3 bytes of a public /24, and then add that onto the end of 233 dot, and then it's basically the first 3 bytes of your IP that you have for /24. So for everyone who has a /24, they have one multicast address that is globally assigned to them. Obviously, it isn't probably going to work over the internet because the internet doesn't natively support multicast, but it is there globally, so you can use it assigned to you for specific use. And then finally, you have a locally significant block. So that is used for inside one specific network range. So in this case, we have the 239/8 range. Don't worry, I won't test you guys on this in the quiz, so you don't need to memorize it. And I wouldn't spend time trying to memorize this unless you need to for exams or something along those lines. So IGMP used to control the membership of certain multicast groups, as I mentioned. It's usually ran on the multicast routers themselves, the routers that run PIM, but you can enable queries on switches, and you can enable, obviously, as we mentioned, IGMP Snooping to run on switches to act as slightly kind of a multicast router to basically prune the traffic where it isn't needed. And as I mentioned, we have a number of versions to IGMP. We have V1, V2, and V3. V1 was the first implementation. It's a little bit bare bones. It does the job, but it isn't perfect. There's many issues, specifically around the time that it takes for a host to leave a multicast group. There isn't any explicit leaves. So that's where V2 came in. It added support for explicit leave requests. So now a host can explicitly say, I don't want this traffic anymore. And from that point on, it doesn't receive the traffic anymore, as long as everything's working correctly. In V1, that would take a while for things to time out. And then the switches and the routers would then no longer forward traffic because it didn't see the requests. We then have V3, which then adds support for source-specific multicast, as we mentioned already, which allows you to source your multicast traffic from a specific source device, which adds a little bit of security, but mainly it's there for where you have say WAN networks where you want to really control down how your multicast is used, where is it from, those kind of things. IGMP messages. We have a range of messages. To start off with, we have the query. This is used to identify by a router what group memberships are requested by hosts. So they can form two types. There's a general query and then there's a specific query. The general query is basically saying everyone, all systems, so it's sent to 224.0.0.1, all systems, the general multicast group, and it says, what multicast groups are you interested in? At that point, you would then also have the memberships reports, which I'll get into a second, and that's how you reply. There is also then group-specific queries. So those group-specific queries are used to basically gather information on a specific group, as it says. The use there mainly is if a host identifies that it wants to leave, you then trigger a group-specific query to say, okay, is there anyone else in this network who is still interested to this network, to this this multicast group? If nothing replies, then a router would prune. So that's why you have the group-specific queries. Now, as I mentioned, there is then the membership report. So this is used by end hosts to report that it's actually interested in a multicast network, or a multicast group, I should say. So by default, usually what a host will do once it joins a multicast stream, it will send out a membership report to say, hey, I want to join this stream, I want to get this content. And it will also use the membership reports to respond to a membership query. Now in V1 and V2, a host will send a message per group it's assigned to. it will also suppress sending those reports if another member within inside the group has responded already. So if you've got 5 devices on the network, 5 end devices on the network, the router sends out a query. Device 1 might send back a report. Device 2 all the way to 5 won't respond because it's already seen the membership report. And that's because the membership reports are sent back to either 224002 if it's a specific query. If it's a specific query, it's sent to the multicast group. If it's a general query, it is sent back to all systems multicast group. If then we are in v3 world, each host should respond to the queries, and each host will respond with multiple reports. So they will group the memberships that they are interested in. Is everyone following along? Because I know I've said a lot of words.
No, cool.
Very
well.
Perfect. So finally, we then have the leave. So as I mentioned in v2, you then add the support for IGMP leaves, explicit leaves. It's used by end host to report very quickly that it wants to leave a group. And the use of this is basically to reserve, not to reserve bandwidth, to save bandwidth and to save processing of a device. If it wants to leave the group, then it needs to leave the group and it doesn't want the traffic anymore. So you add that functionality in with v2 and it's supported based on the leave messages that you have. It's sent to the relevant multicast group as the destination IP address, and it will trigger a group membership specific, what was it called? Sorry, group specific, group specific query, membership query, will be sent by the routers to query the relevant group members to see whether they are still interested and see if there is anything there that's still interested on the network. If nothing is there, then the router will prune and it will stop forwarding that multicast traffic. So moving on, protocol operation. I've gone into this a little bit already, as I mentioned with the messages, but just to give a full overview of everything from start to end, sorry. So when a IGMP router starts up, it will be started in a query mode. And on one layer 3 network, you can only have one IGMP querier. So if there are more than one IGMP enabled routers, what happens is there is an election of sorts. Routers look out for the query messages, and if another router sources a query with a lower IP, that router, the lower IP router, becomes the query for the network. It isn't based on router ID. It isn't based on anything else. It is based on the lowest IP, on the source IP address header for the query that is sent out from the router. Now, once you've got that election, and once the relevant router knows, yes, I am sending out correctly, general membership queries are then sent to start off with more frequently than normal to identify the hosts that are part of a group. So these messages are sent 4 times more frequently than when they are set up by default. So later on, past their initial setup, they are then sent every 125 seconds. Those are the group memberships, the general group memberships queries. That is why when you hear things timing out after, let's say, 4 minutes and 20 seconds, you can put a pin on it and you can say, yes, this is because a device isn't responding to group membership because the default queries are sent every 125 seconds. And so we'll get onto that in a little bit more, but an interested end host will then when receiving that query, will then set a random wait timer, usually 10 seconds, but it is defined in the header of the general membership query. And that basically, as I mentioned, that ensures that only one host on the network replies. So it sets that wait timer before then sending back a response. So if all the end devices responded at exactly the same time, it could flood the router. So that's why we set this random wait time. So then, in theory, statistically, only one device has to respond. Now, when that device responds, it responds back to the relevant group, the multicast group, the destination address, or the all hosts address, depending on the type of query. What that then allows the other end hosts to do is identify if there are other people interested, and it then effectively stops this random wait timer from incrementing and then that end host having to send out a duplicate query. This is then superseded in v3 because all hosts should respond. The idea there is that in v3, IGMP queries can track the state of every individual host. Now, when an end host first joins a group, so you've got, let's say, 5 devices that have already been on the network, already been as part of the multicast group, they will then join the group again. So another device comes online, sorry. It will then join the group. It will try and send another IGMP report message to say, I want to be part of this group. If it doesn't do that, snooping potentially won't work. And if it doesn't do that, then it has to wait for the general membership query to be sent out. So by default, a device will initially send that report message to then initiate all the traffic, regardless of whether there's other devices on the network. And as I said, that just ensures that the first device that is ever turned on into that group actually gets the traffic as soon as possible, because otherwise it would have to wait. Then, if an end host wants to leave a group, it'll usually send a leave message. It can time out, it can just die off silently, but it will send a leave message if it was the last to send a report message. So if others have sent a report message, there's no need, because the routers are basing their forwarding of traffic on that report message that was initially sent. So if you as an end host haven't sent a report message, there's no point for you to send a leave message because the router doesn't know about you. The exception to that is in v3, where the router is keeping track of all of the individual end host states. Now, that leave message should be sent to 224002 or routers rather than the group address, because the other end hosts don't need to know about it, basically. Now, the way that the other end hosts would then ensure that they still get traffic is that, and in the next section here, the router will then send out a group-specific query based on the leave message that you just received, that it just received, because with inside the leave message, it will identify the specific group that it wants to leave. As a result of that, the router will then trigger the group-specific query for that group to check if there's other members still in that. If no one replies, then the traffic is pruned and you stop receiving the stream. Otherwise, it is kept up. If someone replies with a report, then the stream is kept live, and then the process cycles again. The only exception to this, yet again, is in v3, when there's a group-specific query, all v3 hosts will respond. Now, moving on to like the IGMP snooping side of things. Actually, before I go there, did all of that make sense to everyone? Any questions?
Made sense.
Perfect. Mark?
I'm going to forget it by the time we get to the quiz, though.
Cool.
Yeah, it's all good. Good. Thank you so much.
No worries. So, IGMP snooping side of things. A little bit of a diagram here to explain what's going on. There is some switches here which are set up correctly, and there is one switch here which isn't set up correctly. So Here we have an example of where a layer 2 switch is running with IGMP snooping. It has identified that the Multicast source is coming here, and it's also identified that there is a request. Sorry, it's sending the traffic, but there's no one requesting off these hosts, off these switches. So no one's actually requesting the traffic, so there's no need for these switches to forward the traffic down that direction. The reason why this switch is still forwarding the traffic down towards this router is because it needs to go towards the default gateway, which would be here. Now in this section here, we have PIM running. That's a whole different topic. But one of these devices here has requested the traffic via IGMP. The IGMP request would have gone back to its default gateway, and the router would have then started forwarding the traffic based on IGMP, and then also PIM would have enabled the traffic to flow properly. The switch, however, here hasn't snooped any of the traffic, so it doesn't know that only this interface is interested. So what it's doing is flooding out the multicast traffic. Now, that can work perfectly fine. Maybe you're happy with that, but maybe these devices are really old audio devices or really old devices that just can't handle large flows of traffic.
Leave audio out of this.
Sure. Okay. Maybe these are just old devices and they cannot handle large flows of traffic. In the case where this is, let's say, a tag server, for example, it's just requested a 12 gig flow of traffic. If this traffic came into here and then started flooding on this device, and this was a crucial part of your broadcast infrastructure, and it just started receiving 10, 12 gig of traffic, it would probably die. So this is where you use then IGMP snooping to enable your switches to know who is interested in what traffic, basically. Now, how that works is the switches will basically, well, next slide. It technically runs on the layer 2 switches. It's not intended for a layer 3 device, and it tracks the state of IGMP based on inspection of IGMP packets. So it doesn't technically process them, it forwards them on, but it reads them and takes that state and fills out tables and understands it based on what has been sent. So it will read the report messages to understand the host behavior. It'll also read the query messages to see, hey, yes, there is a query, and to suppress any querying behavior. If there isn't a query, though, you can enable a query. So I'll get onto that in a second, though. So when the initial IGMP report messages occurs, hosts always do that, as I mentioned. So that triggers the switch to actually start forwarding the traffic out of the given port, which it's received that IGMP report message. So going back to our quick design here, we've got this host here. It sends out a report message because it's only just joining the stream. This then switch knows, okay, this interface here is interested in that traffic. I need to forward this group out of here, regardless of whether I'm receiving the traffic or not. Regardless of whether I'm receiving the traffic or not, I'm going to forward any traffic for that group out of that interface because someone here is interested. What then happens is you then have the IGMP report messages sent from the routers, and that then queries for the local network, is anyone still interested? If the switch doesn't see anything respond, then the switch will know, okay, no one is interested, prune the ports that are interested in this traffic, and it stops forwarding. Now, obviously, there's the alternative process here where there's a leave message, and that yet again triggers explicitly the switch to stop forwarding that traffic out of that given port that it's received the leave message on. Now, as I highlighted, if you don't have a querier enabled in the network, if you don't have a layer 3 network, if it's just a single layer 2 switch here, you can still enable IGMP snooping. All you need to do is you have a switch that supports IGMP snooping, and you enable it. What that switch will then do is it will act as the IGMP querier. sending out those query messages and responding to leaves or reports. And it then takes up the role of the querier, but then also in the background still taking on the IGMP snooping operations. And that's it. Very simply put, that is IGMP, at least as a good technical introduction.